Electromagnetic Waves by Madelyn Parker. The first step in understanding electromagnetic waves is understanding its two parts, the electric part and the magnetic part. So waves are electric and magnetic because they are a result of the vibrations occurring between these two fields. A scientist named Maxwell came up with an equation to predict this behavior. So he related these vibrations to the speed of light in an equation that's the speed of light equals 1 divided by the square root of mu times epsilon. So mu is equal to the permeability of free space. Now the permeability of free space is a constant that appears between the magnetic flux density and magnetic field strength in a medium. Epsilon is equal to permittivity of free space. This is also a constant that's measured in the farad, and it is a constant that exists between electric displacement and electric field intensity. So Maxwell was able to use this formula as well as 4 other laws that he studied to help us further understand electromagnetic waves. The 4 laws that he studied were Gauss's law of electricity, Gauss's law for magnetism, Faraday's law of induction, and Ampere's law. So Gauss's law of electricity says that the electric flux out of a closed surface equals the charge enclosed divided by the permittivity. Electric flux through a surface's area is rate of flow of electric field through that area times the area of the surface perpendicular to the field. Gauss's law for magnetism states that because magnetic field lines are all continuous loops on a closed surface, the amount of magnetic flux on that surface equals 0 because they cancel each other out. Faraday's law of induction is the idea that when magnetic flux of a circuit changes, there is an electromotive force induced because it opposes that change. So this force is proportional to the rate of change in the circuit, according to Faraday's law of induction. And lastly, Ampere's law relates magnetic field created by electric current, the size of that current, and the permeability of free space. So in essence, electric current is proportional to the size of the current, with the permeability of free space being a variable of proportionality. So from these 4 laws, Maxwell was able to come up with the conclusion of electromagnetic waves. So let's go over what we know about electromagnetic waves. These waves are created by oscillating charge. With these oscillating charges comes an electric field and a magnetic field that make up the electromagnetic wave. The figure below shows this with the electric field oscillating vertically in blue and the magnetic field oscillating horizontally in pink. As we can see from this image, these waves oscillate perpendicular to each other, which means that in most cases, the electromagnetic waves produce a transverse wave. So a transverse wave is a wave vibrating at right angles to the direction it is traveling. So this is depicted in the waves in the rope in the picture below the pink and blue wave picture.
So Maxwell realized that changing electric fields create changing magnetic fields, which then go back to change the electric fields, and this process causes a chain reaction that results in the propagation of a wave like the one pictured in pink and blue.
So the strength of each part of the electromagnetic wave, parts meaning the electric part and the magnetic part, are related by the equation the speed of light, so c, equals the electric field, E, divided by B, which is the magnetic field. From this equation, we can deduce that magnetic field strength is very weak compared to electric field strength, because when you are dividing to get as large a number as the speed of light, which is 3 times 10 to the 8th, your numerator must be incrementally larger than your denominator. Thus, we know that electric field strength is a lot greater than magnetic field strength. Okay, so let's go over the basics of magnetic waves. So wavelength is the distance between equivalent parts of a wave at a single moment in time. So for example, the distance from the peak of one wave to the peak of the next, and this is measured in meters. The period of a wave is the time it takes for a wave to repeat itself. So this is measured in seconds. And then we have the frequency, which is the number of wave cycles per second. So if you look at a certain point, it's the number of waves that pass that point per second, and this is measured in hertz. So the equations in the orange dot on this slide relate these variables together, with F being frequency, T being the period, and lambda, which is upside down Y, being wavelength. So obviously, electromagnetic waves carry energy. So this energy can be absorbed by different objects, such as food in a microwave or skin in a sunburn. The amount or quantity of energy carried is classified as the intensity of the electromagnetic wave. So we can calculate the intensity of a wave using the mathematical equation below on this energy slide. So this equation gives us the power per unit area, which is watts per meter squared as units, with mu, speed of light, and epsilon being values that are given to us as constants.
So here are some practice problems you can do that show you what kind of questions you can solve using these mathematical equations. These use the basic wave equations as well as the equations that we saw on the last energy slide, and then the answers are on the following slides. So here is how you solve 1.1. And then this is the answer to 1.2. And then these are the answers to 1.3 and 1.4. And last but not least, the answer to number 2.
So electromagnetic waves have been classified into a spectrum. This is because they have extremely wide ranges of frequencies and wavelengths. So this forms the continuum for the spectrum. So as seen in the image above, the spectrum ranges from waves with shorter wavelength and higher frequency, which means higher energy, to waves with the longer wavelength and lower frequency and energy. So thus the particular wavelength and frequency is a determining factor in which part of the electromagnetic spectrum a wave belongs to. So this next slide just goes a little bit more into depth on the electromagnetic spectrum. So in the image, we see the differing wavelengths and frequencies that correlate with each type of wave. So the first type of wave are radio waves. This is the wave with the longest wavelength and the lowest frequency, and therefore the lowest energy. And radio waves have a range and of wavelength varying from 3 times 10 to the 6th meters to 3 times 10 to the negative second meters, and a frequency from 10 to the 0 to 10 to the 12th. So you can solve for varying wavelengths or frequency of radio waves, or any kind of wave for that matter, using the speed of light equals lambda times frequency equation. You would use speed of light with the other variable given to you, whether it be lambda or the frequency, and you would find the remaining variable solving algebraically. So the varying lengths is why radio stations have different frequencies, such as 94.1 or 95.5, and these frequencies are measured in megahertz. The next type of wave is microwaves. So microwaves have a wavelength of a few centimeters to a few hundredths of a millimeter, and the frequency is between 10 to the 9th hertz and 10 to the 12th hertz. So microwaves work by heating your food through stimulating vibrations of the molecules in your food, which in turn heat up the food because of this movement of the molecules. So we know that food heats up faster when it has more water in it because the water molecules are able to vibrate more easily. Next on the spectrum, we have infrared waves. So the wavelength for these waves are a fraction of a millimeter to about 750 nanometers, and the frequency ranges from 10 to the 12th hertz to 10 to the 14th hertz. The primary source of infrared waves is heat or thermal radiation. So in the thermal images, like in the picture above on this slide, we see that some objects that emit infrared energy can be detected using instruments. So the color of the object in the picture is a representation of the amount of thermal energy, as you can see from the thermal scale on the side. So how hot something is determined by the picture. So like white and yellow are warmer objects than blues and purples. And then we get to visible light, which have a wavelength of 750 nanometers to 390 nanometers and a frequency of 400 terahertz to 770 terahertz. So visible light is only visible, so you can see it with your naked eye, as part of the electromagnetic spectrum. So because these waves operate on the wavelength and frequency that our eyes can detect, we can see it. Sunlight is primarily the source of the visible range, which is why living organisms can see this part of the spectrum. And the source is electron transitions between atomic energy levels, and that's what produces the light. Next on the spectrum is ultraviolet waves. They have a wavelength range of 400 nanometers to 10 nanometers and a frequency range of 7.5 times 10 to the 14th hertz to 3 times 10 to the 16th hertz. So the sources of ultraviolet waves are electron transitions and sunlight. So this is the source of sunburns. So the ozone layer absorbs most UV radiation from the sun, but if the intensity gets in the harmful range for humans, which is measured in the form of a UV or ultraviolet index, it can cause harmful ionizing radiation, which rips off electrons from atoms and causes skin cancer by exciting DNA molecules. It can also be used for good, though, such as in the use of sterilizing equipment or in the use of vitamin D production. Second to last on the spectrum, we have X-rays. So X-rays operate in the wavelength of 10 nanometers to 0.01 nanometers and a frequency range of 10 to the 16th hertz to 10 to the 19th hertz. So X-rays, as we all know, are used in the medical field profusely. So the sources of these rays are from electron transitions and extreme acceleration of charge. So when X-rays come into contact with our body tissue, they produce an image of our bone because soft tissue such as organs cannot absorb the rays that are at such high energies. So the X-rays pass the soft tissues and give us an image of the bone. So the sources for X-rays are high energy and strong ionizing agents, and they are used in investigation of atomic structures of materials, as well as in airport security and things like cancer treatments as well. And last but certainly not least is gamma rays on the electromagnetic spectrum. They have a wavelength of 0.1 nanometers and smaller, and the frequency is 10 to the 18th hertz and higher. So these waves have the highest energy and the most penetrating radiation, so it can kill organisms, including you, and is often used to treat food to prevent spoilage by killing microorganisms. So we try to stay away from this part of the electromagnetic spectrum. So the sources of this is radioactive decay of atomic nuclei in contrast to X-rays, which typically come from electrons.